Fillers in dental adhesives, composition, functions, and types. Modern restorative dentistry increasingly relies on adhesive systems to create durable bonds between restorative materials and natural tooth tissues. Acid etching of dental hard tissues, particularly enamel and dentin, produces superficial demineralization, resulting in the removal of inorganic minerals and the formation of microporosities within the tooth substrate. When dental adhesives are applied, low-viscosity resin monomers infiltrate these porosities and replace the lost mineral phase. Upon in situ polymerization, the infiltrated resin forms a micromechanically interlocked structure with the demineralized tissue. This phenomenon is known as hybridization, and the resulting interface is termed the hybrid layer. The hybrid layer provides mechanical anchorage between the tooth substrate and restorative materials such as resin composites. Dental adhesives, therefore, serve a dual function, bonding to enamel and dentin, and linking the tooth structure with restorative composite resins or resin cements. Dental adhesives are also widely used in numerous clinical procedures, including direct composite restorations, orthodontic bracket bonding, dental sealant application, root canal obturation, reconstruction of decayed or fractured teeth, aesthetic restorative dentistry. To achieve these functions, dental adhesives are formulated as complex mixtures containing resin monomers, solvents, photoinitiators, inhibitors, and fillers. Role of fillers in dental adhesives. Fillers are incorporated into dental adhesives to enhance their mechanical, physical, and functional properties. Because the adhesive layer forms the critical interface between the tooth and restorative composite, its reinforcement is essential for long-term durability. Major functions of fillers include 1. Mechanical reinforcement. Fillers improve the elastic modulus, bond strength, and durability of adhesives. A reinforced adhesive layer forms a stronger hybrid layer that resists degradation and crack propagation. 2. Improved physical stability. Filled adhesives exhibit increased hardness, reduced water absorption, improved dimensional stability, lower susceptibility to hydrolytic degradation. 3. Viscosity modification. Small amounts of filler increase the thickness of the adhesive layer and prevent excessive thinning during application. A slightly thicker adhesive layer with moderate elasticity can better absorb stresses generated by polymerization shrinkage of the overlying composite. 4. Functional properties. Fillers may impart additional therapeutic or diagnostic properties, such as radiopacity, fluoride release, antimicrobial activity, remineralization capability. To achieve efficient stress transfer between filler particles and the resin matrix, fillers are often silanized using coupling agents such as gamma-meta-acryloxypropyl trimethoxysilane. Silane coupling promotes chemical bonding between inorganic fillers and the organic polymer matrix, improving mechanical strength and preventing premature degradation. Influence of filler size and content. The particle size and concentration of fillers are critical parameters in dental adhesive formulations. Particle size. Fillers must be sufficiently small, often in the nanoscale range, to penetrate dentinal tubules and the interfibrillar spaces of demineralized collagen along with resin monomers. Excessively large particles hinder infiltration and compromise hybrid layer formation. Filler loading. Adhesives generally contain low filler content. Excess filler increases viscosity and reduces surface wettability, limiting penetration into the etched tooth substrate. High viscosity may also interfere with polymerization kinetics and decrease the degree of curing. Therefore, an optimal balance between reinforcement and flow properties must be maintained. Additionally, the colloidal stability of filler particles in the adhesive formulation is crucial to prevent sedimentation and ensure homogeneous dispersion. Inorganic fillers. Wollastonite. Wollastonite, calcium silicate, is a biocompatible filler commonly used in dental materials. It exhibits favorable mechanical properties and low shrinkage. Because it contains calcium ions, wollastonite can release Ca2+, promoting mineral precipitation and collagen remineralization at the dentin interface. This process stimulates apatite formation and enhances bond durability. In photocurable dental adhesives containing approximately 2Wt% wollastonite, ultimate tensile strength increases from about 34.9 MPa to 46.0 MPa. The filler typically appears as needle-like particles dispersed within the resin matrix. Montmorillonite nanoclay. Montmorillonite, MMT, is a layered silicate nanoclay with plate-like particles and a high aspect ratio. It is widely used as a reinforcing nanofiller to enhance mechanical properties. To improve compatibility with organic resin matrices, MMT is often modified through graft polymerization with monomers such as methyl methacrylate, methacrylic acid, acrylic acid. Grafted polymer chains increase the interlayer spacing of clay platelets, preventing aggregation and enabling better dispersion. Adhesives containing modified nanoclays show improvements in elastic modulus, flexural strength, diametral tensile strength, microshear bond strength. Surface modification also enhances colloidal stability and reduces sedimentation. Niobium pentoxide. Niobium pentoxide, NB2O5, is an emerging filler with promising bioactive properties. When exposed to saliva, niobium pentoxide can induce hydroxyapatite crystallization, leading to mineral deposition on the adhesive surface. This filler exists as a stable monoclinic crystalline phase and diffuses into the hybrid layer after application. Its presence improves NUP micro-hardness, radiopacity, polymerization kinetics. Because niobium pentoxide increases adhesive viscosity, it restricts radical mobility and reduces bimolecular radical termination, thereby accelerating polymerization reactions. Tantalum oxide. Tantalum oxide, TAR205, is another bioactive filler with excellent biocompatibility, radiopacity, and chemical stability. Tantalum has a strong affinity for phosphate ions, facilitating apatite deposition and promoting osteoblast attachment. Nanoparticles of tantalum oxide are often silanized using gamma-methacryloxypropyl trimethoxysilane before incorporation into adhesive resins. Increasing filler content enhances radiopacity and improves fracture resistance by inhibiting crack propagation. Adhesives containing about 10 Wt% tantalum oxide nanoparticles demonstrate improved resistance to hydrolytic degradation and enhanced microtensile bond strength. Silica. Silica is one of the most widely used fillers in dental materials. Incorporation of silica particles into dental adhesives improves mechanical strength, bond strength, resistance to polymerization shrinkage. Silica particles are inherently hydrophilic and therefore often treated with silane coupling agents to improve compatibility with organic resins. Surface modification reduces interfacial energy and enhances filler dispersion. Mechanical properties such as flexural strength and microtensile bond strength generally increase with filler loading up to an optimal level, after which further addition leads to property deterioration. Porous sintered silica nanoparticles produced at high temperatures, 1300 degrees C, possess surface porosity that promotes micromechanical interlocking within the cured adhesive matrix. However, silica alone does not provide sufficient radiopacity. Therefore, mixed fillers such as barium oxide, silica or ytterbium oxide, silica are often used. Nanoparticle-based fillers. Hydroxyapatite nanoparticles. Hydroxyapatite is the principal mineral component of enamel and dentin, making it an ideal biomimetic filler for dental adhesives. Nano-sized hydroxyapatite particles penetrate dentinal tubules more effectively than larger particles and contribute to the formation of a composite hybrid layer. Hydroxyapatite nanorods formed by directional crystal growth exhibit improved mechanical performance and good colloidal stability. Optimal filler loading ranges from 0.2 to 0.5 Wt%. At approximately 0.2 Wt%, diametral tensile strength reaches a maximum, approximately 34 megapascals. Higher concentrations may lead to nanoparticle agglomeration and reduced curing efficiency due to increased opacity. Hydroxyapatite nanoparticles also demonstrate bioactivity, promoting remineralization of demineralized dentin and interacting with collagen fibrils at the adhesive interface. Surface silanization further improves adhesion to the resin matrix. Zirconia nanoparticles. Zirconium dioxide, zirconium oxide, is a ceramic widely used in dental applications because of its high strength, fracture toughness, fatigue resistance, and biocompatibility. When incorporated as spherical nanoparticles in dental adhesives, zirconia acts as a reinforcing filler and increases tensile strength. The presence of zirconia also enhances bonding to dentin. However, its high hardness may contribute to wear of opposing teeth. Hybrid fillers such as zirconia silica nanofibers have been developed to improve performance. Gold nanoparticles. Gold nanoparticles possess excellent chemical stability, biocompatibility, and antimicrobial properties. They can be incorporated into dental adhesives as colloidal dispersions. Increasing nanoparticle concentration improves flexural strength and diametral tensile strength by inhibiting crack propagation. However, excessive loading may cause particle aggregation, creating stress concentration sites that initiate cracks. Gold nanoparticles also demonstrate potential for bone regeneration, which may contribute to tissue healing around restorations. Boron nitride nanotubes. Boron nitride nanotubes, BNNTs, consist of strong BN covalent bonds and exhibit exceptional chemical stability. Their fibrillar morphology and hydrophobic character provide several advantages in dental adhesives. BNNTs can induce mineral deposition, reduce water infiltration in demineralized collagen, enhance solvent resistance, increase the degree of conversion and polymerization rate. These properties contribute to the long-term durability of adhesive bonds. Glass-based fillers. Pre-reacted glass ionomer fillers. Pre-reacted glass ionomer, PRG, fillers are produced through an acid-base reaction between polyalkanoic acids, e.g., polyacrylic acid, and fluoroluminosilicate glass in water. Depending on the extent of reaction, two types exist: full pre-reacted glass ionomers, FPRG, surface pre-reacted glass ionomers, SPRG. The reaction forms a siliceous gel that is subsequently dried, milled, and silanized to produce filler particles. Adhesives containing about 17% PRG filler show strong adhesion to enamel and dentin and release fluoride ions that diffuse through the adhesive interface. Calcium-containing PRG fillers, PRGCA, can also be used in light-cured adhesives. Fluoride release increases with filler content without significantly affecting the polymerization of resin monomers. Bioactive glass. Bioactive glass, BAG, fillers typically contain approximately 65 moles% silicon oxide, 31 moles% cal, 4 moles% diphosphorus pentoxide. These materials release calcium and phosphate ions that promote remineralization of dental tissues. In addition, ion release increases the local pH, creating an environment unfavorable for bacterial growth. Phosphate-based glasses represent another class of bioactive fillers capable of controlled degradation. They can be doped with metal oxides such as copper oxide to impart antibacterial properties. However, filler particle size must be carefully controlled. If particles approach the wavelength of curing light, they may reduce the degree of polymerization of light-activated adhesives. Conclusion: dental adhesives are sophisticated multi-component systems designed to create durable bonds between restorative materials and natural tooth tissues. The incorporation of inorganic, nanoparticle-based, and glass fillers plays a crucial role in enhancing mechanical performance, polymerization behavior, and long-term stability of the adhesive interface. Fillers not only reinforce the adhesive matrix but also provide additional functional benefits such as bioactivity, remineralization, antimicrobial activity, and radiopacity. Advances in nanotechnology have enabled the development of novel fillers, including hydroxyapatite nanoparticles, nanoclays, metal oxide nanoparticles, and nanotubes, that significantly improve the durability of dental restorations. Careful control of filler size, surface chemistry, dispersion stability, and loading level is essential to maintain optimal viscosity, infiltration capability, and curing efficiency. Continued research into bioactive and nanostructured fillers is expected to further improve the performance and therapeutic potential of modern dental adhesive systems.